Imagine waking up tomorrow morning, you reach for your phone to check your messages, but the feed won't refresh. You try to pull up Google Maps for your commute, but the screen stays blank. You go to buy a coffee, and your card is declined. Not because you're out of money, but because the entire global banking system has just gone dark. In a matter of seconds, everything we take for granted, from emergency services to the power grid, could be cut off from the rest of the world. In an instant, the modern world as we know it has simply stopped. Most of us believe our digital lives exist in the cloud or are beamed down from satellites orbiting high above. But that is a dangerous misconception. The real heart of our civilization isn't in the sky, it's buried in the mud of the ocean floor. The true threat to our way of life isn't a hacker in a dark room or a sophisticated cyber weapon. It's a physical incident occurring 5,000 meters below the waves in total darkness far beyond our reach. Much like the silent U.S. nuclear submarines that reposition within striking distance of key targets to maintain global deterrence, there is another invisible force patrolling the abyss. Thousands of miles of fragile glass threads are currently resting under crushing pressure, silently carrying the lifeblood of the American economy and the survival of global communication. These are the subsea fiber optic cables, the literal nervous system of our planet. We are living in an age where our entire existence depends on a network we can neither see nor touch. A single severed connection at a strategic point could trigger a devastating digital collapse, paralyzing nations in minutes. But how does a cable no thicker than a soda can carry the weight of all human history and every single byte of data we generate? And how do we keep this massive infrastructure running when it's hidden in the most hostile environment on Earth? Let's take a closer look at how this works. To understand why this system is so critical, we have to look at its sheer, overwhelming scale. Let's take a closer look at how this works. Most people assume that satellite technology is the backbone of our digital age, but in reality, satellites handle less than 3% of global data traffic. The other 97% is screaming through a massive underwater web that spans the entire planet. Right now, as you watch this, there are over 1.4 million kilometers of fiber optic cable snaking across the ocean floor. To put that in perspective, that is enough cable to wrap around the entire Earth 35 times. If you were to stretch it out into space, it would reach the moon and back 4 times over. This isn't just a network. It is the largest, most complex piece of infrastructure ever built by human hands, and yet almost no one ever sees it. The strategy behind this massive expansion has developed over many years. Historically, these cables were owned by consortiums of telecommunication giants like AT&T or Verizon, but recently, we've seen a dramatic shift in the underwater empire. Today, the race to own the ocean floor is being led by a new breed of superpower, big tech. Companies like Google, Meta, Amazon, and Microsoft have realized that owning the pipes is just as important as owning the data. By building their own private subsea routes, they aren't just renting space from telcos anymore, they are becoming the landlords of the deep sea. But what exactly does one of these cables look like? Interestingly, when you see a diagram of a subsea cable, you might expect something massive, like a pipeline or a subway tunnel. But the reality is far more surprising. Most of the cable resting in the deep ocean is barely the diameter of a standard soda can. In fact, in the deepest parts of the sea, where the threat of human interference is low, the cable is even thinner, closer to the width of a Sharpie marker. It seems impossible. How can something so small gang vac or carry the weight of billions of people's data? Let's compare this to a person to help us visualize. If a single human represents 1 byte of data, then one of these cables is carrying the entire population of the planet every single second. It is a masterpiece of mega-scale engineering where the giant-in-a-box concept is taken to its extreme. You have a tiny physical footprint carrying a massive world-altering load. Of course, getting these cables to the bottom of the ocean is a feat of engineering that borders on the impossible. This is where the true beasts of the operation come into play, the cable-laying ships. To help us understand the volume of this operation, you have to look at these vessels. These are no ordinary ships. A modern cable layer is a specialized monster, often reaching the length of 2 football fields. Inside their hull, they carry massive circular tanks called pans, which can hold thousands of miles of cable coiled in perfect, intricate layers. Just like an aircraft carrier is the core of a strike group, these ships are the center of a global operation. But while an aircraft carrier is built for power, these ships are built for a strange combination of massive strength and surgical precision. Imagine trying to lay a thin thread on the floor of a dark, windy room while standing on top of a 10-story ladder that is constantly shaking. Now imagine that thread weighs thousands of tons, the room is 5 miles deep, and the ladder is a ship being tossed by 20-foot waves in the middle of the Atlantic. That is the daily reality for the crews of these vessels. They must operate with the precision of a surgeon. If the ship moves too fast, the cable could stretch and snap. If it moves too slow, the cable could bunch up and tangle on the jagged rocks of the ocean floor. The computers on board have to calculate the ship's position, the tension of the cable, and the terrain of the seafloor in real time, 24 hours a day, for months at a time. All in all, there are only about 50 of these highly specialized ships in the entire world. They are the silent guardians of the internet, working in the most remote corners of the globe to ensure your Netflix stream doesn't buffer and your bank transfer goes through. The cost of this operation is equally staggering. Commissioning a new transatlantic cable can cost upwards of $300 million to $500 million. Adjusted for the complexity of the environment, building these underwater highways is often more expensive and dangerous than building a skyscraper in the middle of Manhattan. But for companies like Google and Meta, it's a price they are willing to pay for total control over the global flow of information. As we move away from the frantic pace of global politics and corporate races, we start to enter a quieter, more mysterious realm. Because once that cable leaves the ship and disappears into the dark blue, it enters a world of extreme pressure and freezing temperatures. Has to survive for at least 25 years without a single human ever touching it. This endurance is one of the most incredible parts of the story. To understand how these cables survive, we have to look past the scale and start looking at the microscopic level. We have to peel back the layers of this soda can and see the high-tech armor that keeps the world connected. But what's actually inside these cables? How does a tiny strand of glass carry a laser beam across the entire ocean without losing its signal? In the next section, we are going to explain the complicated anatomy of a subsea cable in super basic animation. We're also going to analyze how a robot LANSO or deep sea rove operates at depths where the pressure would crush a human like a grape. And most importantly, we'll see how engineers perform open-heart surgery on a broken cable miles beneath the surface. Stay tuned, because we are about to go inside the X-ray of the most important machine on the planet. To truly understand the genius behind this technology, we have to look inside the X-ray of the cable itself. To simplify it for animation purposes, we'll divide the cable's anatomy into 5 main sections. Section 1 is the outermost layer, consisting of a thick jacket made of high-density polyethylene. This is essentially a heavy-duty plastic shield that protects the interior from the abrasive saltwater and the jagged rocks of the ocean floor. Section 2 lies just beneath, where we find a layer of mylar tape and stranded steel wires. These wires provide the massive tensile strength required for the cable to be pulled through the ocean without stretching or snapping under its own immense weight. Section 3 consists of an aluminum or copper water barrier. This is a critical line of defense. If even a single drop of seawater manages to penetrate this layer, the entire cable could short-circuit. Interestingly, this metal layer also serves a second purpose. It carries the high-voltage electricity needed to power the signal boosters along the route. Just below it is Section 4, a hard polycarbonate tube filled with a protective petroleum jelly. This gel acts as a cushion, protecting the delicate center from the extreme crushing pressure of the deep sea, pressures that would instantly collapse a standard hollow pipe. Finally, we reach Section 5, the heart of the machine. This is where the actual data travels. Inside the gel are several strands of optical fiber, each no thicker than a human hair. These are made of ultra-pure glass, so clear that if you were looking through a block of it miles thick, it would still appear as transparent as a window. But there is a strange problem engineers had to solve. For years, reports suggested that sharks were strangely attracted to these cables, often biting into them and causing massive damage. To help us understand why, we found out that the high-voltage electricity running through Section 3 creates a faint electromagnetic field to a shark. This field mimics the electrical signals given off by wounded prey. It's a biological glitch that nearly took down the early internet. Today, engineers use additional layers of specialized steel armor to ensure these vampires of the deep can't sink their teeth into our data. But how exactly does a tiny strand of glass carry information across 5,000 miles of ocean? In this video, we're going to explain the complicated process of fiber optics in super basic animation. Imagine a tunnel lined entirely with mirrors. If you shine a flashlight into one end at a specific angle, the light bounces off the walls, zigzagging all the way to the other end without ever escaping. This is called total internal reflection. In a subsea cable, lasers pulse on and off billions of times per second, sending bits of data through these glass tunnels at nearly the speed of light. Now that we've mastered the basic anatomy, let's look at the step-by-step process of how this nervous system is actually installed on the seabed. Step number 1 is the sonar survey. Just like a nuclear submarine uses sonar to map its surroundings, the cable ship uses a multi-beam echo sounder to create a high-resolution 3D map of the ocean floor. Engineers must find a path that avoids underwater volcanoes, deep-sea canyons, and unstable fault lines. Step number 2 involves the sea plow. This is a massive robot LANSO, or ROV, that is lowered from the ship. As the ship moves forward, the plow is dragged along the bottom, carving a trench about 3 feet deep. The cable is fed through the plow and buried instantly, protecting it from fishing nets and anchors, the leading causes of cable damage. Step number 3 is the deployment of repeaters. Because light loses its strength as it travels through glass, engineers must install repeaters every 30 to 50 miles. These are massive, torpedo-shaped cylinders that weigh over half a ton. Inside, they contain sophisticated optical amplifiers that catch the weakening laser signal, boost it back to full strength, and send it on its way to the next continent. But what happens when something goes wrong? This brings us to the most incredible part of the story, the twist that most people never consider. When a cable breaks in the middle of the Atlantic, you can't just send a diver down 5 miles to fix it. The pressure at that depth is over 10,000 pounds per square inch. It would crush a human like a grape in a fraction of a second. Instead, engineers must perform what can only be described as open-heart surgery on the ocean floor. First, the cable ship uses its sonar to locate the exact point of the break. Then, they drop a specialized grapnel hook, a massive steel anchor designed to snag the cable. They drag the hook across the seabed until they feel a catch, and then they slowly winch the broken end to the surface. This is a grueling, high-stakes process. Once the 2 broken ends are on the deck of the ship, engineers enter a climate-controlled clean room. They must strip back all 5 sections of the armor, find the hair-thin glass fibers, and fuse them back together using a high-precision laser welder. Each fusion must be perfect. Even a microscopic speck of dust could ruin the connection. This process can take over 15 hours of continuous, focused work. Once the surgery is complete, the cable is wrapped in a new protective joint and lowered back into the abyss. All in all, it is a testament to human ingenuity. We have taken the most fragile material on Earth, glass, and buried it in the most hostile environment on the planet to ensure that you can stay connected. From the multi-beam sonar mapping the dark mountains of the abyss to the laser welders performing surgery on the deck of a tossing ship, every byte of data you send is supported by a global army of engineers and a massive invisible machine. This approach to building and maintaining the subsea network is a vital part of our global survival. But while we focus on the technology, we often forget the human element. The crews who spend months at sea, often in dangerous conditions, to keep the guard or guardians of the internet standing watch. As we look at the complexity of this machine, we move toward a deeper appreciation for the silent infrastructure that holds our world together. In the final section, we'll see how this all connects back to you. All in all, the next time you send a simple text, make a bank transfer, or watch a video like this one, remember that your data is traveling through a world of extreme darkness and crushing pressure. It's important to realize that the internet is no ordinary cloud floating harmlessly in the sky. It is a fragile physical reality. Network of glass threads thinner than a human hair, resting on the mud of the abyss. This infrastructure is a living machine that requires constant, vigilant protection to keep our civilization from falling into silence. We should never underestimate the endurance and sacrifice of the crews who maintain this invisible nervous system. These are the silent guardians of the digital age, working 24/7 aboard specialized vessels in the most remote corners of the ocean. They operate in treacherous conditions, performing surgical repairs miles beneath the waves, all to ensure that your world stays connected. Their work is a testament to what human ingenuity can achieve when we push the boundaries of engineering. We make original 2K animations from scratch with a very small team working on it full-time to bring these hidden worlds to light. We also produce original engineering and geopolitical content designed to simplify the most complex systems on our planet. If you found value in this analysis and want to see more, please subscribe and hit the notification bell so you don't miss a beat. Your support is what keeps this channel moving forward. Thank you for watching.